This is the first on what's going to be 3 videos on aldol reactions. Okay, if you recall back to the video that we had on picking bases to make the enolate, if we wanted all enolate, we need to use a particularly strong base, like sodium hydride or LDA. If we used a weaker base, like hydroxide or an alkoxide, an equilibrium would form where it have significant amounts of both the enolate and the aldehyde present. And in that case, because the aldehyde is electrophilic and the enolate is nucleophilic, the enolate can react with the aldehyde in what's called an Aldol addition reaction. And the reason we call it an aldol is because we have both an aldehyde and an alcohol, so aldol. And the alcohol in these aldol addition reactions always ends up on the beta carbon. Okay, so let's take a look at the mechanism for these aldol addition reactions. So we're in basic conditions, so the enolate is going to be the reactive intermediate. So the first step is to create that intermediate. So we start with a proton transfer, where we're pulling off one of the alpha hydrogens. Right now, this enolate is resonance stabilized, so we also have the resonance structure with the negative charges on the oxygen, but we're interested in carbon attacks, so that's why we're showing this particular resonance structure. So the nucleophilic center on the enolate attacks the electrophilic center on the aldehyde, right? And part of the reason we're so interested in this is because this forms a new carbon-carbon bond. And then the last step is to protonate and give us the alcohol using water as the proton source. All right, now this reaction generally does not go to completion. It's an equilibrium process. Now, for most simple aldehydes, the aldol product is favored. But for most ketones, the aldol product is not favored, and the yields are relatively low. And the ketone, the starting material, is in fact favored at equilibrium. Now, in this case, the reverse reaction actually has its own name. It's called a retro-aldol reaction. And the mechanism is just the exact reverse of the aldol addition. So in the aldol addition, we end with protonating the alcohol. So the first step in the retro-aldol reaction is deprotonating that alcohol. Right? Then instead of nucleophilic attack, we have the loss of a leaving group, giving us back the enolate and the, in this case, ketone. And then the last step being reprotonating the enolate to give us back the ketone starting material. Now, another reaction that can happen along with or immediately after an aldol addition is called an aldol condensation. And so if we heat the aldol product, we can eliminate the hydroxy group to give us an alpha-beta unsaturated carbonyl group. So we can eliminate this OH with heat, and this gives us the alpha-beta unsaturated carbonyl group. And I feel like I'm repeating myself, but this happens when we heat the aldol addition product. So to get this aldol condensation, we first undergo an aldol addition to give us the aldol. Then if we heat it, we can eliminate the OH and give us the aldol condensation product. All right, so if we consider the total mechanism for the aldol condensation, I think it's easiest to break it up into 2 parts. Right, the first part is simply the aldol addition, which is the first mechanism we saw in this video. And the second part of the mechanism is what's new, and it's just 2 steps. So first we have a proton transfer. And unlike the eliminations that we saw back in Chapter 7, where we had, say in an E1 mechanism, we had a carbocation intermediate. In this case, we have a carb anion intermediate. And normally, a hydroxy group is a bad leaving group, but because I have this anion, that's what makes the hydroxy group now able to be ejected as a leaving group. And so, because the carb anion is relatively unstable, right, it forms the pi bond at the same time that the hydroxy group leaves. Now, generally, these aldol condensation products are going to be, we're going to have unsymmetrical alkenes, and so we're going to preferentially form the alkene that is less sterically hindered. So we would rather have the E isomer rather than the Z isomer. Now, we mentioned that the yields are generally relatively low for the aldol addition products, especially if we're starting with a ketone. And so sometimes, and maybe oftentimes, it is difficult to isolate the aldol product, and it goes directly to the aldol condensation product. That is especially true in this case, where this alkene that I'm forming has a lot of conjugation between both the pi bond of the carbonyl group and with the pi bonds in the benzene ring. And so this greatly favors the formation of the aldol condensation product if there's if I can have lots of conjugation on the alkene I'm forming by eliminating the alcohol. Okay, and this is really just a follow-up on the last slide. The aldol condensation product is obtained at high temperatures. So if I want to try to get the just the aldol addition product, I would do it at low temperatures, and because this is a ketone, the yields are going to be relatively low. But if I want the aldol condensation product, I can run the reaction at high temperatures, and in that case, the percent yields are relatively good. So we're going to continue talking about these aldol reactions in the next video, and then after that I have a video with some example problems on some of these reactions.